In prior videos, we looked in section 4.4 at families of functions that had parameters in them. And one interesting family of functions were called the logistic functions or the logistic model. And that function looks particularly like y is equal to L divided by 1 plus some number a e to the minus kt. Okay, and in this video we're going to tie in section 4.4 and 4.5, L'Hopital's rule, together and look particularly at a function of this logistic type. Okay, so here is an application of a problem that appears in the L'Hopital rule section. It says that we're looking at W for wolf population, so this is the wolf population at any time t. Okay, and there are some constants k in them, and we can see that the constant k is given by 252 in this problem. There's a number r in this problem. Right here there's a parameter r, which is 0.283, and then we have time t equals 0 represents the population in the year 2000. So t is equal to 0 is essentially the year 2000. Okay, and we are being asked to compute this limit. Okay, now there are a couple of ways to approach this problem. The first problem is just to go straight up at this problem and just say, oh, we're computing a limit just like we would any limit. So we can compute the limit as t goes to infinity of this constant k, whatever it is, e to the rt. K and r are given, so we know that r is positive and k is also positive. And then we have k divided by 40 plus e to the rt minus 1. So we can try to just compute this limit straight up, and we notice that as t goes to infinity, because r is greater than 0, we know that e to the rt goes to infinity as t goes to infinity. So we're seeing that this numerator is getting really big. Okay, the denominator, we're seeing that essentially we have k over 40, which is just a constant, minus 1, also a constant. We're going to have some sort of constant plus e to the rt, which is going to go to infinity as t gets really big. So what we're seeing here is an indeterminate form, infinity over infinity, okay? In which case we could tackle this problem using L'Hopital's rule, okay? So we would have to compute the same limit as t goes to infinity, take the derivative of the top function. Remember, this r appears because of the chain rule. The derivative of the bottom, k over 40 and 1 are constant, so their derivatives go away. It becomes 0. The derivative of e to the rt is r e to the rt. And because of a little bit of algebra, e to the rt's cancel out. R e to the rt cancels out, and you're left with only the constant k. And this limit as t goes to infinity of that constant k is the constant k. All right, so we've figured out that this limit is equal to k, and then the next thing you would need to do would be to interpret your answer. Okay, and this is where it's helpful to have some context behind the function that we're talking about. And this is a wolf population as a function of time. And as time gets really big, as time keeps going on and on and on, we're finding that the wolf population doesn't just continue to grow without bound, but it actually levels out and approaches some constant k. Okay? So that's doing the straight up problem, evaluating this function as t goes to infinity. There is a slightly other way to look at this problem, and I'm going to copy this problem down on my paper here before I go to the next page. Right? And there was, let's add a page below now. We could have looked at this problem, limit as time goes to infinity, of the function k e to the rt divided by k over 40 plus e to the rt minus 1. Okay. We could have, just before we just jumped right into doing L'Hopital's rule, we could have tried to do a little bit of algebra on this problem, right? And the algebra would look like trying to factor out the e to the rt. Okay, so if you factor out e to the rt from the top and the bottom, factoring e to the rt out of itself leaves 1, and then we have this constant k over 40 minus 1, and we factor e to the rt out of that, and that means we'll get minus e to the negative rt. You can check yourself there by distributing the e to the rt back through, and that bottom term right there will be e to the rt. E to the rt times e to the negative rt is just the constant, right? Because e to the rt multiplied by e to the negative rt, you get to add the exponents, which gives e to the 0, which is 1. So the interesting thing about this problem is that just by doing a little bit of algebra, we can see that this function that we were asked to compute the limit of is equal to k divided by 1 plus k over 40 minus 1 e to the negative rt. So that is the function we were asked to compute the limit of. Now if you compare to the functions that we've already looked at before, recall that the logistic function, or the logistic model, a function was a logistic function if it was of the form some number divided by 1 plus some other number e to the negative rt. Okay, and if you look back at the way they wrote it before, this number in the top they would have called L, and instead of star they would have called that the number A, e to the minus rt. So what we can see here is that in terms of the wolf population problem, they're using the constant k instead of L, and L is something called the carrying capacity. This is the carrying capacity of the population, and we can see that this is going to make sense because we know that as t gets larger and larger, e to the negative rt is going to get smaller and smaller and go to 0. No L'Hopital's rule needed, right? So the algebra helped us out of this problem. And we can see here that this limit of this problem, okay, as you put a limit as t goes to infinity, that this limit is going to be k, just like it was before. And k, in this case, is the carrying capacity. So the wolf population has some sort of limit. When there's logistic growth, you know that there is some sort of maximum population that is sustainable. Okay, and we can see here what this function is going to look like if we bring up our Desmos graphs. Sorry, let me bring up Desmos. Okay, and then we will move this to our screen. So here we can look at a typical logistic function. It would be y is equal to L divided by, or let's look at the wolf population problem. It was k divided by, we decided that it was 1 plus k divided by 40, k divided by 40 minus 1 multiplied by e to the negative rt. times r. And let's see, we want this function to be a population w as a function of t, and so that there are only two parameters in this problem, k and r. So we'll add parameters for those. And let's see, we wanted the k value not to be 1, but we wanted it to be a much smaller number. Okay. And k was going to be a large number. I think we had, let's have k going from 100 up to, I think we decided that the population k they said was 252. Oops, sorry. K going from 100 up to 252. Okay. So here we're starting to see a population, and r was a small number. Okay. And here is what a typical logistic function is going to look like. Right? As you adjust the t value, okay, can you see here the k value is 100, and you can see our population at time t is equal to 0. The population is about 40. Okay, and then as time goes on, right, the population starts to increase, but then it levels out to whatever this k value was. And so as I change the value of k, the shape of the graph is going to not change a lot. It's going to keep its general shape, but the only thing that's going to happen is that the function is going to level off at whatever value of k is here. So when k was 252, oops, k is 252, right? You can see the function leveling off around 250, and then I can't remember the value of r. I think our value of r given in this problem was 0.283. So this r value, adjusting it, is going to control how quickly you can make it a small number, 0.01, that will eventually get up to 252, but we'll get up there slowly, so the population isn't growing very fast. But the bigger the number, the quicker we get up to 252. And for this particular problem we were looking at, r was equal to 0.283. Okay? So there's an actual problem where L'Hopital's rule might be needed, and in the context of a problem that might have some meaning. So ends this video.